I just want to talk a bit more about Enrico's garden. He's a very broad mathematician, contributed broadly and very deeply all over. Also an artist, as you know, actually a professional artist. And like his art, Enrico's papers are written with great care, detail, clarity, beauty, and of course, not least, mathematical brilliance. I think that we really lack that kind of writing, and it's becoming less and less prevalent amongst young people who are uploading and everything in a big hurry. If you read a paper of Enrico, you see that there's so much thought that's been put into it before he writes it, just like a piece of art. Everything fits in the right place. You can see that there's been a lot of labor. And I think that kind of style is far too few people do it. Yeah.
I learned a lot from that.
Okay. Yeah, Davenport has a similar feature. Yeah.
Maybe someday someone qualified should write, update how to write a paper now that you can use computers, like that, how to adjust references, how to use references. And writing a paper is not just writing down your own idea.
Okay, I'm going to get to that. I'm going to get to that.
Often,
He's very careful with that. Not everybody is, as we know. So in the Rubenstein Commons over here, you will find some posters of mathematicians who've made pieces of art of some formulae, which Enrico has one, which I'm going to explain in a minute. It's one of the the poster that we used for the conference. And this was, I think, initiated by Daniel Rockmore and I think given to Enrico, and Enrico gave those 5 of those, or I think all of them that he had anyway, to the Institute, and they are posted in the Rubenstein's Commons. So any of you not seen that, you should go there and you'll see the original of what I'm going to show you now, which is this poster, which I'm going to actually talk a bit about the math on this poster. It's Rey groups. I hope I'm pronouncing it, Rey groups. Why did it change color? Yeah, doesn't matter. I guess when I point. So there are a lot of equations there. I want to explain what that is. So these equations are concerned with one of the most difficult parts of the classification of finite simple groups. Specifically, there are these low-rank groups called Rey-like groups, which when you, in this classification theory, which is very elaborate and complicated, you of course use Silo theorems and many tools invented by people like John Thompson, who I'll mention in a second. And there are these groups called Rey-like groups, which have no subgroup of index. These are simple groups, of course. They have no subgroup of index 2. The Silo 2 subgroups are all abelian. And there's involutions. There is an involution inside the group T, for which the centralizer of T is isomorphic to the T times SL2 FQ, where Q is some prime and prime power. And one seeks to show that if Q is bigger than 5, and you have such groups, Rey-like groups, they must be of the form Q must be of the form 3 to the 2n plus 1. And if that happens, then there are such groups, and that's why they're called Rey groups, which were found by Rey using exceptional group G2 and some twisting. He constructed this sequence of infinite sequence just for Q prime 3 to a power, an infinite sequence of simple groups. So when you are doing classification of simple groups, you work out conditions of the group, and eventually you try to show that you're one of the ones that you have. And then, of course, there are sporadic ones. This is a big industry still going on, I believe. Anyway, the key workers on this part, and this, by accounts that I've looked at, is one of the most difficult cases in the classification, were works by Ward and John Thompson, especially by John Thompson. And he reduced the problem to this set of equations. So it's not so clear. I hope you can see it. Unfortunately, I'm using just a camera to take the picture, but I wanted to use Enrico's art and math done same time. And these are the exact equations that Thomson produced. So firstly, before Enrico, if you want to see the story about Enrico getting into this, he says he knows nothing about finite groups. Don't believe that. He's not an expert in finite groups, and he got interested in this, I think, through discussions with, according to what you write in this Rutgers lecture, maybe 8 years ago, through Thomson, who interested you, and Gorenstein, Daniel Gorenstein, who was at Rutgers and, of course, was very involved in this classification of finite groups project. And so they already knew that Q had to be a power of 3, as you can see, 3 to the 2n plus 1. The automorphism, that T becomes this automorphism sigma, an automorphism of the Galois group of FQ. And then there are some unspecified from this group theory construction for the array type groups. You have these integers A and S that are written here, which satisfy some condition. And then you get these 4 conditions where Z, Y, and U is not in the field F3 itself, some condition like that, satisfy this set of equations which defines a curve. And so you would expect some number of solutions over FQ here, but then you have this extra equation which involves these unspecified A's, and that extra condition is supposed to be very harsh. And these conditions, if you can prove that under these conditions, the automorphism sigma must square to the Frobenius 3 itself, then you prove the ray type group is a ray group and you've classified as you desire. So Thomson had reduced it to this, and according to Enrico, they suggested that at this point somebody from outside the field should take a look at this, and Enrico, who is a problem solver of the highest caliber, got interested. And he solved this problem. And let me just say a few words about what he did. So these are equations. Sorry, I'm going the right way, but I went back. So Enrico's idea, as you might expect, and I think they understood this as well, is that if you try to count the original set of equations, you more or less know how many they are, but the extra condition should force you to have fewer solutions, and so that either sigma squared equals 3, which is what you're trying to show, or this integer n must be limited. That's the starting point. And so he starts to eliminate variables and tries to make this feasible. And I won't go into it, but I would say that every description I've seen of this is it's an ingenious series of successive eliminations, finally arriving at either sigma squared equals 3, or the n is not too bad. In other words, Q is 3 to the 2n plus 1, and 2n plus 1 is less than 83, which is already feasible. In this lovely lecture paper that from only 7 years ago, he explains how he came up with this and how repeated applications and the equations become very complicated, but how the use of elimination leads to this feasible computation. And then that was left with these limited number of cases that today may be a walk in the park for computers, but this was quite a while ago. So, of course, he contacted Odlitsko, who can compute pretty well at the Bell Labs, and his fellow Hunt, and it shows that sigma cube must be 3, and thus solving this. All ray type groups are ray groups, thus solving this considered most difficult case, or one of the most difficult cases of the classification. Thomson's work is, of course, very important. So this result has considerable, so this is what Hunt writes in the review of Enrico's paper. This result has considerable importance in the classification of finite simple groups. Ordinary mortals, such as the present reviewer, are overawed by the author's tour de force. Many people are overawed. But I wouldn't call Enrico tour de force. It's always, when you read it, you understand it. He once told me there's 2 kinds of mathematics, the one I haven't read and what I've read. And I've understood, the one that I haven't read, now that's always true. The one that I haven't read.
Little comment.
Yeah.
I discussed this problem with Thomson, and he showed me how he had reduced to finite
Big number.
calculation. The size was, or the calculation was about 3 to 600.
Which was not feasible.
which is not feasible. So, but I'm not the guy that gives up. So 133, the dream said, Enrico, you're stupid. Let me try to write the formulas. Why the property or the formula follow the property, the transformations you have to do. Don't even try to write the formula, but follow the property. And after that, it worked 9 months non-stop on the problem, and found a way to do it.
Yeah. I will return to this determination in a second. I'm going to talk about an elephant in the room. All right. I just want to give you, when we say Enrico works with great effect on different fields, this is his PhD thesis, the local Bieberbach conjecture, which was cited in his field method, actually. And I remind you what this is. So the Bieberbach conjecture, formulated by Bieberbach, is if you have a univalent one-to-one analytic function in the unit disk, and it's state 0 at 0, and you normalize it so it starts with the coefficient 1. So it looks like z plus a2 times z plus a3 times z, a2 times z squared plus a3 times z cubed. Then there's an inequality on the univalence implies this inequality. Sometimes variants of this are written down, but I'll follow what Enrico writes in the Inventiones paper, which I believe is his thesis. That the real part of an is less than or equal to n with equality unless f is the Kober function, z over 1 minus rho z squared, where rho to the n minus 1 for the nth coefficient is 1. So often people put absolute values here, but since Enrico is trying to identify the extremal function and prove locally it's extremal, so this was the achievement of this paper, is he was able to prove that if you're close to the Kober function, then the Bieberbach is true. So before Enrico's work, Bieberbach himself, this is just very simple, using area considerations, proved that the conjecture for A2. Loebner made a major breakthrough. He proved it for n equals 3. This is the paper in which he introduces the Loebner differential equation that today goes by the name of the Schramm-Loebner equation in mathematical physics. Loebner introduced it in order to prove the Bieberbach conjecture, and it's a deformation which preserves, from which you can derive these inequalities on the coefficients. And he did 3. My memory is actually that called on the Bieberbach conjecture 1, because Bieberbach told him that, of course, you'll do the general case in the next paper, but then they got stuck, and nobody could ever push this through. Beyond that, people found ways of doing 4, that more maybe Schiffer and people like that. But let me explain this Bombieri theorem, 1967, which was at the time and remained until the problem was solved, the best result, and that is locally it's true. So if the A2 is near 2, so we know A2 and A3, it's true for those, so this denominator is positive. And so if you're very near 2 with A2, then you have corrected all the other coefficients. If you're very near 3, at A3, you corrected all the other coefficients. And the n odd and even on n odd is a much more difficult case. And that's what Enrico really achieves here. And he uses Loebner critically. He deforms near the Kober function using the Loebner deformation. That Loebner deformation, as I say, is one of the most important things. Of course, in the end, he's now proving a local theorem. So in the end, he's got some inequality he has to prove, and it's some quadratic form on the function space L201. Of course, he's done all this calculus of variation before. This is a very natural thing. But to proving that a quadratic form on an infinite dimensional space is positive definite means basically you have to understand it and diagonalize it. And he does that. That's what the achievement is here. So his theorem was for many years the best we know towards Bieberbach. But then in 1984, it was quite unexpected. The branch gave a complete proof of the Bieberbach conjecture. And his proof basically boils down to applying Loebner's method. Loebner's method is so powerful, but not to the coefficients a n, but you first exponentiate this, and there's a new inequality called the Milling-Lebedev inequality, which people had not really tried to use Loebner because Loebner didn't work. He got stuck on the original problem. But it's, as you all know, that if you're trying to prove something by induction and you carry the wrong assumption on each term, somebody comes in and whispers, no, prove more. And that's what happened here. And so much so that there's actually a one-page proof. Conjecture, if you assume Lerner's method and you prove the Milling-Lebedev, and it's due to Leonard Weinstein, 1991. And it's one page in a big journal. So that problem has been solved. Okay, of course, Enrico's worked on zeta functions for well over 50 years. So we can see the results, but that's clear. And his results, and Henrik was mentioning this, like the large serpent, says that the Riemann hypothesis is true on average in many different forms and shapes. And it serves as a complete substitute for the Riemann hypothesis in some problems. That's what Henrik was joking, saying, well, essentially it's proved. Well, that's a bit of an exaggeration because there are problems where on average, it's not enough, many problems. But I'll give you one example of where it's not, when I say you prove something complete by the substitute. It's not that you improve some exponent somewhere else. That's less interesting. You actually completely resolve a problem. And there's a problem that Enrico resolved. I don't know if you know, but I'm going to give you a present today. You solved the problem. You're the first person to prove arithmeticity. So Selberg formulated arithmeticity in higher rank. And Margulis is very famous for resolving that in general. But Selberg actually did prove one case, and that's the case of product of SL2Rs, product of upper half planes, at least two upper half planes, irreducible lattice quotient, which is finite volume but not compact. In that case, he was able to prove in the early 60s that the group has to be arithmetic, but he had to assume the Riemann hypothesis, the generalized Riemann hypothesis. And the minute Enrico's paper came out, he could have added at the bottom corollary. You're the first to complete. Of course, Selberg and Enrico knew that, but they didn't even bother to point that out to everybody. So that did not go noticed for a long time. All right. So while working on GRH and uncovering these very complicated needs, I think it's fair to say, for those of us who know Enrico well and talk to him a lot, he's never shied away from tackling this problem head on. So that he's put in tremendous efforts, and I'm sure will continue to do so. The way I like to say it is he leaves no stone unturned on any idea that might have some chance on this problem. And if somebody comes with an idea, he's got a rule on this or any other problems that people might send to him. 3 strikes and you're out. 2 strikes and you're out. It could be anybody. They send him a proof of Riemann, he'll take it very seriously. You'll read it, you'll write back. If it comes back nonsense, 2 strikes and you're out. But the first strike is always giving open to anybody. And I've seen that when it comes to chosen. Of course, he's got his own ideas. And this is something that he's put more effort into than, I mean, many people have tried, but I don't know. It's quite an effort. Now, in the setting of a function field, I'll be almost over here, over finite fields, as we know, just for curves over finite fields, they prove the Arden's analog of the Riemann hypothesis. And Enrico has, of course, studied this inside out and given many, many very masterful accounts of this. In particular, the same time when he was at Collège de France, I think he gave a seminar Bourbaki on Stepanov's elementary proof. And Enrico's treatment is so crystal clear that it just shines out of the page. It's short. He follows this polynomial method, as combinatorists like to call it today, which is the basis of all Diophantine approximation, to give upper bounds, and then the Riemann for curves follows from that. But I want to point out, this may be not so well known. There are many problems, and I and Gilbert have been involved in some of those recently, where even in this function field, these elementary methods give you upper bounds, which are much stronger than the Riemann hypothesis. Even if you know the Riemann hypothesis, they're much stronger. And it's not just a matter of improving something, it's actually decisive to solve the problem completely that's at hand. So these elementary methods actually are, I think, extremely important, and Enrico is critical in making these understood. Alexa I should know, it's my student. I mean, last year, one Princeton's undergraduate valedictorian writing a senior thesis based on Enrico's treatment of Stepanov. And I told him I'm going to introduce him to Enrico, and he did, and he came here and met Enrico for lunch. It was a lovely lunch, and then he had to run off to give his 2003 graduation speech to 2,000 people. Enrico's, of course, a master, understands immediately when things, when there's progress. I'll say a word about that in a second. His book with Walter Gubler, was awarded the 2008 Duke Prize. Ehrenberg mentioned that earlier. The book's called Heights in Diophantine Geometry, and from the citation, the book is a research monograph on all aspects of Diophantine geometry from the perspective of arithmetic geometry and transcendental number theory. The key emphasis is on the delicate theory of heights, which is developed with extraordinary precision and elegance. The book is a masterpiece in terms of its original approach, it's very original, and its unrivaled comprehensiveness and sheer elegance of exposition. There can be no doubt that this book will become the basis of future developments of the central subject in modern mathematics. That's certainly true. By the 100th page, you've got a proof that's really originated by Voiter, but first recognized quickly by Enrico as being a correct proof. I can tell stories about that too, of Voiter, who came with the Diophantine approximation proof of the Mordell conjecture. And that's in the book. I'm finishing now. It's telling me to stop. Okay. Subspace, it's a book that I've taught out of. It's fantastic. So looking back 50 years to the citation from Enrico's Fields Medal. By the way, the other recipient of Fields Medal 50 years ago was David Mumford, with whom Enrico wrote a few papers on characterization, classification of surfaces and characteristic P, quite natural given Enrico coming from the Italian geometry school. And in Enrico's citation of his Fields Medal, it says, Bombieri's versatility and strength have combined to create many original patterns which are both rich and inspiring. I would say the last 50 years, they've only amplified these words. And here's Enrico at Mumford, 1970. Thanks.